Okay, so hello, how are you? So thank you for watching this class lecture video. So this this Monday I cannot come to school because I just had my another eye have surgery, so I cannot drive. So I have to use this lecture video. So I'm sorry for the inconvenience, and again, thank you for watching this video. Okay, uh, so we say the once we have data, we can do the two things: estimation, find confidence interval, and also do hypothesis testing. So let's check this problem. So testing problem is just if we don't believe other people's claim, so we will check data. Right? So for example, let's consider this problem. For me, I claim my students like my teaching, and at least 70% students like my teaching. Okay, so I claim 70%, or at least 70%. But our department chair don't believe me, right? So he wanted to conduct a survey, or just check some people, check 100 students. Then find only 65 students say yes or like my teaching. Okay, so here we have some difference percentage. So I claim is 70%, 0.70, but from data only 65%. So we have a 5% difference. So we need to determine this difference is big difference or small difference, right? So how to determine this? So we say at first we change this to standard difference. So change this says 70 to 0, then this number 65% becomes this number. So we call this as a Z value or T value or test statistic. So this test statistic is just uses the formula x bar minus mu 0 over sigma of radical A. Right? So here, so we can plug in here is x bar. We can regard this x bar 65 or proportion percentage, right? Minus mu 0 is 70%. And sigma, so for here, sigma is 10, yes or no question, 10. So sigma is radical PQ. So let's say, so P, we have two P's. I claim P is equal 70, and from data, so this is my claim. From data, this is 65. So we denote this 65 as P hat, meaning from data. Okay, so this sigma is PQ, square root PQ. So which P we should use? So here we should use 70, right? Yeah, because this, I claim this is 70 is from population. There's so 65 is from data. So there's PQ, then over AN is 100, right? So this is test statistic. So then what? Okay, yeah. Okay, so we find this number is this equal this negative 1.05. So we just changing this difference from 70% to 65% to be 0 to negative 1.09, right? So we wanted to determine their difference is big or small. So we have two ways One way is we use p-value. Okay. So what is p-value? So this z value, so means we need to check z table, right? So this z table, this 0, this negative 1.09. So this is p-value. So we just check this p-value is larger than this p-value is small or not so small. Okay, so compare with alpha is 0.10, right? So we just check this from the z table, we can find the p-value. And also we can find the cutoff point or find the critical value. So we call the z critical value. We just check, let's say we can find this z critical value. The critical value like this. We just from this z table, we find this cutoff point such that, so this is, we should use such that this probability is, let's say, so 0.10. So this is one tail or two tail. Sometimes we got confused. So one tail, two tail depends on what good meanings. Good, not so good. So here we're talking about my like a percentage for like my teaching. So high is good, low is not so good. So not good, we just need to check one side, right? So here we just check one tail. One tail, so 0, 0. One tail, 0.10. So we just check one tail. We just check this. Let's say this is equal 10%. So what is this cutoff point? So we need to check here. Let's say from the table we check this. Like, okay, this is 0.10. So we need to check this cutoff point such that all the way down is 90, right? So we just check where is 9000. Okay. So from the z table, I believe this cutoff point should be 1.28, right? I think this is 1.28. Okay, so this is negative 1.28. Okay, so then we determine this over test statistic, negative 109 is big difference or small difference. So we say our cutoff point is thus. This is negative 1.28. So we just use negative 1.28 as our standard. So source number, we say small number. Source number, big number, the big difference. So we find, oh, negative 109 is here. So we can say this number is small. Or difference is small. So we cannot, let's say, so the department chair cannot reject my claim, even though they have 5% difference, but this 5% difference is not so significant. Okay. So there's a testing problem, right? So we say basically testing problem is just to check whether test statistic and the critical value. There's a two-way. We just use this critical value to determine the test statistic is big or small. Okay. So we say in statistics, we have the table here. So in statistics, we say we want to judge HO, HA, so we make a decision. But in stats, no decision is 100% true, right? So when we reject HO, maybe this is a mistake. we still have some chance of a mistake. Maybe our decision is wrong, right? Maybe HO is we should not reject. Okay, and we accept HO, maybe also a mistake. We should not accept HO, right? Okay, so when we make a decision, we will have some mistake. So what kind of mistake we can make? So actually, like we just focus on HO, like HO, other people's claim. So for their claim, for this HO, we for other people's claim, we can accept it, or we can reject it. So our mistake can be like this: we reject HO when we should accept it, right? So this is a mistake, and we accept HO when we should reject it. So we have these two kinds of mistakes. So we call these mistakes as type 1 error or type 2 error. Type 1, type 2. So this is today's topic. So type 1 or type 2. Today's topic is type 1, type 2 errors. Okay, type 1, type 2. So the question is, so which one is type 1? Which one is type 2? So we can so which one is which one is type 1? Which one is type 2? This is actually up to us. This is just the name, right? Okay, so we say determine which one is type 1, which one is type 2. We say it's up to us, but we have to follow the tradition, other people, right? We follow other people. So how can we? So roughly we can say type 1 error is of a forced reaction. Like let's say for other people's claim, our forced reaction should reject. We don't believe them, right? Only we have enough information, only we believe this guy is very trustable, then we can believe this guy's claim, right? So for other people's claim, our first reaction should be reject. So sometimes we reject it is wrong, so we call this reject HO when we should accept it. So this is type 1. Okay, so this is type 1. Okay, type 1. And this one we accept it. We accept it. HO means we easily to believe other people. So this is a type 2 error. Okay. So compare the two mistakes. Usually, type 2 error is more serious. So like you are easily to believe other people. So this is a big mistake. Okay, so we can say that type 2 is more serious. Okay, so why we say this more serious? Let's check this situation. Originally, we test other people's claims. Or original questions check the medicine. So some people claim, some people say, "Oh, our medicine is good." Right? Medicine is good. Okay, so this is their claim. So for this claim, we can first one we do not trust them. So we will make those mistakes, right? We refuse. We do not believe them. Actually, we should believe them. Meaning, actually, the medicine is really good. So our mistake is we refuse good medicine. And type 2 is we easily believe them, but actually their claim is wrong. So let's say they say their medicine is good, so we just believe them. So we buy their medicine and take the medicine, but actually the medicine is bad, not so good. So this mistake is we just take bad medicine. So refuse good medicine or take bad medicine. Take bad medicine is more serious, right? So we say usually type 2 error is more serious. Okay? So we say for other people's claim, our first reaction is refuse, reject their claim, don't believe them, right? So only if we have enough evidence or enough information, then we can believe them, right? Okay. So this is type 1 error, type 2 error. Okay. So instead, we set the HO is other people's claim usually. So we say type 1 error is we refuse HO when HO is true. Okay, type 2 error is we accept HO when HO is not true. Okay. Okay. So let's say for decision making rule, before we use p-value, we say if p-value very small or p-value, how can we say p-value small? We just compare p-value with this significance level alpha with this alpha. If p-value less than alpha, then HA, right? Or HAO, reject HO. So what alpha is? So we say alpha is significance level. But what is significance level? So we mention this like if we say if we want to make a conclusion at 90% confidence. So 90% confidence level. So here we have a confidence level. So 90% confidence level means our conclusion has a 90% chance to be true, to be correct. So we say 90% confidence level almost equivalent to significance level is this thing, right? So we can understand that this significance level is the probability for making mistake. Like 90% chance my conclusion is true, then this also implies 10% chance my conclusion is wrong, right? So this alpha is significance level. So what is significance level? So we say more precisely, this significance level is the probability for making mistake. So we have two mistakes, like type 1 error, type 2 error. So now we can say more precisely, this alpha is type 1 error. Alpha is the probability we will make those mistakes, type 1 error. Okay? Okay. So let's say, so before we make our decision based on p-value, but actually what we need is just check whether the significance, whether the test statistic is a big number or small number. So let's say to determine so here's 0, okay. To determine this number is a big number or small number, we just need a cutoff point. Like let's say, suppose 1.69 is this big number or small number? This depends. If our cutoff point is 1.8, we just set this cutoff point 1.80. Then we say 1.69 is a small number. Okay, so if we set the cutoff point as 1.5, we use 1.5 as a cutoff point. Then we say, 1.69 is a big number, right? So this depends on our cutoff point. So once we have a cutoff point, we can make a decision. We can judge this number is big or small, right? Okay. So let's say, so our decision-making rule is just that once we have the cutoff point, then we can make a decision. Okay. So now let's consider this example. Okay. So some people claim this mu average is at least 3.00, with sigma is 0.3. So this is some people's claim. Okay. So we wanted to test this claim. So we intended to collect some data. So make a decision, or we can use a p-value. So but the p-value got confused. What is p-value? What is the p-value confused? So we make things very simple. I just ask somebody to do that. Please check some people. Let's say check 25 people randomly. Check 25 students, and so find their average. So our decision-making rule. So I just put the cutoff point is thus. Let's say they say at least the 3.0. So I just put 3.0 as a cutoff point. 3.0. So we put a cutoff point here, the 2.85. So if x buys this part, 2.58. If less than 2.85, we will reject the claim. We will believe average GPA cannot be so high. So if above, let's say, if above 2.85, like here, or here, then we just accept the claim, right? So our decision-making rule, once we have the cutoff point, then the decision-making rule is very, very easy, very clear. Everyone can make a decision easily based on this, right? We don't need some knowledge for statistics. So just like I tell you, I ask 25 students, I check 25 students, and find their x average, find the sample mean. Then based on sample mean, we can make a decision, right? Okay, so for this decision, we want to check this decision is good. So how can we determine this decision making rule is good or not so good? So we find, let's say, we want to find alpha. Okay, so check this. So basically, we say if alpha is alpha is small, then we can use this decision making rule. If alpha is big, like 20% or 30%, then this means use this decision making rule to make our decision. We have 20% chance or 30% chance to make a mistake. So this 20% or 30% is too high, right? So this means, this decision making rule is not so good. We should not apply this rule. Okay. So now let's consider the problem. So find alpha. So alpha is type 1 error. So what is type 1 error? So we just remember refuse HO when HO is true. So refuse HO is, so we say when x bar less than 2.85, x bar is here, we will refuse. So when HO is true, we just put mu equals 3.00, right? So when mu equals 3.00, so when mu equals the same, find the probability. So we need to know the distribution for x bar. So we know x bar follows this normal distribution mu and sigma our radical n. So in this case, we say mu is 3.0, right? And sigma 0.3 and n 25. Okay, so we know the distribution exact. So distribution x bar is this. Follow this normal means 3.00, standard deviation 0.06. Okay, so now we need to find the probability x bar less than 2.85. So such a problem become easy, right? We just need to find a probability about the normal distribution. So we just say first round changing this to standard normal, so minus mu divided by sigma, and a little bit of calculation, we find a 2.50. Then we check z table, find this probability. Okay, so okay, 0 cut point negative 2.50. So we need to find this probability. But the normal table we can only find, we can only check 2.50, right? So this probability is just 1 minus equal 1 minus. So we just check 2.50 from Z table. Okay. From Z table, so let's say, so we have Z table here, 2.50. So I just check 2.50. I think we have Z table here. Okay, yeah. So I check 2.50. 2.50 is this 993A. So our probability is for this one is 1 minus 993A, right? Okay. Okay. Yeah. So this is just 1 minus 993A. Okay. So this equals 0.000062. So we say there's a probability really, really small. So this means, apply this decision making law to make a decision, almost no mistake, right? Okay. Okay. So here we say once we have cut point, then we can find alpha. We can judge whether this decision making law is good or not so good. So a little bit confusing thing is sometimes we just check one side or one tail. Sometimes we need to check two sides, right? So the key point is what is good or not good meanings. So sometimes good means the higher the better, the good, right? For example, our GPA or our salary, right? Or like the high the good. So for our cost, the low is the bad. So in those problems, we just check one side, right? So sometimes precise means good, not so precise means not so good. Like our blood pressure or our weight, too overweight not so good. Like too skinny is also not so good, right? So the two sides, or one side, or two tail, one tail depends on, should we consider two tail, or two sides means not so good, or just only check one side? So let's consider this problem. Let's say 10 years ago, those people, so we talking about weight. Okay, weight for the mean is this, standard deviation this. So this standard deviation we say from 10 years ago from the our record. So this is about information for population. We say mu is 163, sigma is 7.2. So we want to check whether people's weight has changed. So we consider whether they have some change. We don't care increase or decrease. So here we say we talking about whether close to this number no change or have change. So the have change means either side is change, right? So here we should consider two tail. Okay, so to determine this, we can we just pick a data. We were intended to check 100 people, and so we make a decision like this. So, if the average weight close to 133, then we say no difference. But 10 years later, so all people's weight today and 10 years ago, no much difference. And so on both sides we say have a difference. So here we can put a cutoff point. We can put a cutoff point, two cutoff point, like here's 162 and 165. So we say in this part and this part, if x bar is too low and too high, we believe they have a difference, right? Okay, so based on this decision making law, we want to find alpha. What is alpha? Okay, so alpha is top one arrow. So alpha, we remember alpha is refuse HO when HO is true. We don't believe, we refuse, right? So refuse HO. So we can say this range between this range here is accept HO. We say no difference. Then other side have difference. So other side we will refuse. So refuse HO means x bar larger than 165 or x bar less than 162, right? So in this case we will refuse HO. So when HO is true, means mu equal 163. So we want to find this probability. So such a problem is just like so we need to know the distribution for x bar. So let's say so x bar follow this normal, right? Mean by now means 163. Mu thus then sigma over radical n. So here, okay, so let's check out. So we need to find what is sigma, what is n. So let's go back to the problem itself. So what is sigma? What is sigma? Sigma 7.2. What is n? N is 100. So here is 7.2 over 100. Take square root of 100, right? Okay, so this distribution, so we say just this. X bar follows this normal. Mean is 163. So standard deviation is 0.72. Okay, so now the problem become like x bar follow this normal. We need find the probability that x bar larger than 165 or x bar less than 162. So we have two parts, right? So equal, so this is probability plus this probability. So then this probability we just change to standard normal. So minus mu divided by sigma. So here the minus mu, again minus mu divided by sigma. So then by now we need a little bit of calculation. So changing the find, so let's see what is this. So 165 divide this 2 over this. So then like so here just a little bit of calculation. So once we have this, like let's say, so cut the point, then find the probability. So we need use table. So 1 minus this probability 1 minus the number from the table, right? So the tables give us only left side. Yeah. Okay. Okay. So we can find this probability. So this probability is the alpha is the probability that we may make those mistakes based on this decision making law. Okay. Okay, so now let's say, okay, so let's check some other examples. So we say once we have cut point, then we can have a decision making law. So we need, let's say, we need check whether the decision making law is good or not so good. Right? So let's consider this problem. Like this guy, so we wanted to check whether this guy will win the election. Okay. Or whether we can predict this guy will lose the election. So our decision making law is just like that. Okay. We will check 1,000 people. If more than 510 people will vote for him, then we will believe this guy will win. Okay, so the cut-off point is like say, we just change this to percentage. Cut-off point is 0.51. Okay, so if here we will believe this guy will win. Okay, we will claim this guy will win. Okay. Okay. So now let's say, so based on this cut point, so we want to find alpha. So alpha is this. We say refuse HO when HO is true. So here we need to specify what is HO, what is HA. So we're talking about this guy will win or this guy will not win. So win means like his percentage or proportion will larger than 50. Okay, right? So this means win. So here, so HO, so HO is not cannot win. So here we say HO, we just put HO as equal. So P equals 0.50. This is HO. Okay. HO is non-hypothesis is always equal. Even though this guy claim I will win the election, so this guy's assumption or claim is actually is P larger than 50, right? More than half. But we always set the HO as equal. So P equal 0.50. So HA is HA is P percentage larger than 50. So we can believe this is when HA is he will win, HO is still half chance. So we cannot say he will win, right? Okay. So this alpha is refuse HO means we believe he will win. So when we will believe he will win, so when P hat larger than 51. So when H was true, meaning percentage actually is just half, P equal 0.5. Okay, so find the probabilities. Again, so we need to know what is the distribution for P hat. So P hat is just like X bar, right? So P hat follows this normal, like just this mu sigma over radical n. So for this case, mu is just the P, and sigma this is PQ, right? Square root of PQ is sigma n. Okay, so here what is okay? So what is P? So we say, oh, if HO is true, then this means P is 0.5, and PQ so 0.5. P now Q is also 0.5. PQ and square root of 1000. So X bar follows this normal. Okay, so P hat follows this normal. So X bar follows this normal. P hat follows this normal. Right? So more specifically, we have the P hat follows this normal. And then so find the probability. So become like P hat follow this normal. We find there's a probability. So such a problem is just a regular problem. Right? We changing to standard normal, saying we find it. So this equal like in order to check a table, so we just need 2 decimal digits. So we just change this as larger than 0.63. So we just check let's say check 0.63. So check 0.63, but we focus on this part, this probability. So we need 1 minus here, 1 minus. So we just check 0.63. So let's just say 0.63 for standard normal. Okay, 0.63 is 7357. 7357. Okay. Okay. So this equal 7357. Okay. So this probability equal, let's say this equal 2643. So this alpha is quite big. We say we have so this is 26% is quite big, right? So this means based on this decision-making rule to make our decision, we have about 26%, 25% chance for making mistake. So this is easy to understand. Like here, the story just like that. So here's only half, like 50. So stories. if 50-50, then still have half a chance. You cannot predict this guy will win. So here 51 a little bit higher than 50. So you claim, oh, you're so excited. You claim, I will win. I will win. But just let's say, but some people will say, oh, wait. You should not claim so quickly, because you just hide only 1% high, right? So this is not enough. Okay, just slowly, just like that, right? Okay. Okay, so we say like so here, so we have another question like this cut point not so good. Then we can say like if we put 1% high, we claim maybe it's not so good. How about 2% or 3%? Maybe 3%. It will be safe for me to claim I will win, right? So here's another story: is we want to find a reasonable cut-off point or decision-making rule. Okay, so let's say let's stop here and then continue. Okay, because I don't want to make the video too long. Okay, so make the file too big. Okay, so let's stop here and we will continue. Okay.